Another piece of evidence, and this one is, really damning. Large moving shadows. Here is one of the two astronauts on the surface of the moon at any given time. The third astronaut was orbiting in the command module. It's actually the command slash service module, but it's usually just called the command module. But anyway, so a crew of 3 Apollo astronauts each time, 2 on the surface and 1 orbiting. There's the one astronaut, and a little further away is the second astronaut, and this is all being remotely filmed from a camera on the lunar rover. Now notice this fringe here, and here, these color fringes. That's called color banding, and that's a phenomenon in photography. It's not all that uncommon, and it occurs sometimes when objects and shadows move across the scene, and that's where that color is coming from, just so that you know, so you're not confused. Now, watch what happens here as the camera films is focused on this distant astronaut. You have 2 shadows quickly passing in succession. Okay, I'll run it backwards. There's one, actually that was the second one, and there's the first. And with the color banding. All right, 2 shadows quickly pass across the entire scene, including that astronaut. And here it is in black and white. What could that possibly have been? There is nothing on the moon, living or not, that is moving. The only thing that would have been moving on the moon at that moment would have been those 2 astronauts, and as you can see, they're pretty still, okay? Because whatever caused those shadows happened very quickly, because you can see that the astronauts aren't even moving. They're pretty much frozen. All right. There cannot be such shadows on the moon, since the 2 astronauts are the only moving objects there. There is nothing, quote unquote, flying in the moon's sky, except the orbiting command module, which, being so high and small across the face of the sun, would not cast a shadow at all, much less appear and in these shapes. Something clearly passed across the moon set's floodlight. And that's because they were in a studio on a moon set, not on the moon. And here is a real killer. We're running into, there are a lot of killers here. This one pretty much slays the Apollo mission. This is this one is going to be specifically Apollo 11. Okay, before we get into that though, let's look at some footage of spacecraft orbiting planets. Okay, this is the shuttles orbiting Earth. Okay, planetary objects. And these are 5-second intervals for each of these frames from this video. And you can see that things move very quickly. Okay, I should have actually done that more smoothly. Things move very quickly out of the field of view, and certainly out of the center of the field of view. Nothing stays put, okay? Because any spacecraft orbiting Earth or the moon would be moving literally thousands of miles an hour. It's not hanging around. This is allegedly a spacecraft, the Selene. I think it's the Selene Moon Explorer or whatever it's called, orbiting the moon. Now, I have serious doubts about the authenticity of this. This terrain, I think, is fake. But certainly the orbital motion is realistic. Okay, so let's go through that. Now watch that big crater coming from the top. Okay, I'll run through it one more time. Again, things are moving quickly out of the field of view. Even within the field of view, they're moving very quickly. Okay. And then finally, here's an Apollo 10. Here's footage from Apollo 10, which preceded Apollo 11. And here, things move out of the field literally in 2 or 3 frames. Within 3 frames, things are gone. You can hardly even keep track of them. All right, we're talking about just seconds, just a few seconds in any given in the field of view for a particular object. Now this is a footage. This is footage of. This is supposed to be live footage of Apollo 11 as it was starting to orbit the moon when it first arrived there. And so I'll read this. A live broadcast of the Apollo 11 spacecraft allegedly orbiting the moon for the first time. The craft's movement shown here is nothing like the completely smooth, unidirectional motion of the craft in the preceding videos, where things on the ground very quickly moved out of view. Imagine a rifle bullet with a tiny camera on it. And as a matter of fact, the Apollo 11 spacecraft was supposedly orbiting the moon at twice the speed of a rifle bullet. And here's Frank Reynolds and his sidekick analyzing and commentating on what's going on. And I'm going to run through just 3 frames quickly. And these, like the others, are all 5-second intervals to show you a couple things. First of all, look at the quality of this video. It's ridiculous. Why couldn't they show you clear pictures, something like these from the lunar orbiter spacecraft, or one of the lunar orbiters, which orbited the moon and took photographs before Apollo. Okay. Secondly, I want to orient you. This is Haldane crater here, and this is Schubert and Bach. Okay, these are going to be the craters we're going to focus on at first. Haldane, Schubert, and Bach. Okay, so now let's watch what happens. There's Haldane, a very unique-looking crater, and here's the larger scene. There's Haldane, Schubert, and Bach, and then they're going to move from top to bottom here, which is actually from east to west. Okay. All right. Finally, let's go through the scene. Now, notice how erratic the motion is. They're zooming in and out, so that confuses things even more. But what I want to really point out is how long those 2 craters, Schubert and Bach, these 2 craters here, were in this field of view. They were in that field of view for 3 minutes. Okay, I'll speed up to get to the beginning again, and we'll see. I'll show you again. Okay, here's the first frame where Schubert and Bach are clearly in the scene, in the field of view. Okay, the field of view is simply the distance across this window that they're looking through. Okay, so there's Schubert and Bach at the bottom, and they're going to stay there. Actually, they're going to skip over to Haldane, going in the wrong direction, by the way. But when they come back down, they're still over Schubert and Bach. There's Schubert and Bach near the top there. There it is in the middle again, going back to the top. Finally, they leave Schubert and Bach. And this is an impossibility because they couldn't have hung around over those 2 craters for 3 minutes. Here's Schubert and Bach, and together they're 60 miles in length from both of them together are 60 miles in length. The field of view is only twice that distance, which is 120 miles. Schubert and Bach are 60 miles. Okay, and the orbital speed is 1 mile per second. Okay, 3,600 miles per hour, which works out to 1 mile per second. So that field of view that they were looking at should have and would have been covered in 120 seconds. Okay, 2 minutes. Instead, and you can go back and look at the times, but I've already done that, they covered it in 180 seconds. They took a full minute too long to cover that ground. And compare the length of time for any given object in the same field of view for the space shuttle, 30 seconds, Selene, 20 seconds, Apollo 10, 10 seconds. Okay, so here's an illustration of what's happening. The field of view is 120 miles. Okay, we can measure that. I did measure that. So in 100, and because the speed is 1 mile per second, in 120 seconds, they've gone 120 miles, and they're looking at an entirely new field of view with an entirely new set of objects. There should be nothing in, if this is the second field of view, there would be nothing in it. They would have been from the first field of view, I'm sorry. Okay, an entirely new field of view. They went not only 120 seconds, they went 180 seconds. They supposedly would have moved 180 miles. All right, so they would have left whatever was here at first in the field of view long. They would have left it a long time ago. All right, Schubert and Bach would no longer be in the field of view after 120 seconds, much less 180 seconds. The spacecraft stays over crater Schubert and Bach, moving only very gradually for 3 minutes, an impossibility given what should be its extremely fast and constant orbital motion. In reality, the two craters would have disappeared from the field of view much sooner, after 2 minutes. Continuing, the spacecraft then sits completely motionless, an even more flagrant impossibility, directly over another crater, starting at this time here, an hour, 13 minutes, 30 seconds, for a minute and a half. Overall, the spacecraft's motion is ridiculously erratic, both in speed and direction. Clearly not orbital motion at all. So we're going to continue, okay? And now we're going to be over these 3 craters here, or this set of craters. Okay, that's going to be what's prominent in the field now. All right, so here we were, or they were, Schubert and Bach were at the bottom of the field of view. They moved to the top of the field of view because they're moving, now the spacecraft is over here, and now it's going to be over these 3 craters, and it's going to continue moving west. So watch what happens here. They sit over that crater for a while. Now watch this crater right here. Okay, it's going to move into the center of the field of view, and watch what happens after that. There it is in the center of the field of view. It stays in the center of the field of view for a minute and a half. It doesn't move at all. In other words, the Apollo 11 spacecraft is not moving until finally they leave. They hovered over that crater, which is a complete impossibility because there is no hovering in orbit. It's like a rock flying around the moon. It's literally, that's what an orbit is. Okay, and they had no technology to be hovering over the moon. They were showing us, what they were showing us was filming of a model. They were not orbiting the moon, period. Okay, moving on to the moon environment. And first we want to consider that the moon sits in an almost perfect vacuum. And I want to make this note. One of the keys to pulling off this deception by NASA is that the moon is a vastly distant alien place, totally inaccessible to non-astronauts, the perfect place about which to concoct a fairy tale. And for us, this is the key to unraveling the deception. To test NASA's story, we have to start not with the bogus material they provide us, but with our known Earth experience, as well as what we already know about the moon from solid scientific and astronomical knowledge independent of Apollo. So we're going to start with Earth. That's going to be our ground, so we know what reality is like. And this is a four-wheel drive car, a Subaru, in fact. And what this video shows is, I'm going to just show you frames from the video, is rocks being sprayed in an arc away from the tire. And the interesting thing is that the rocks trace a shallow arc straight back. And in the video, especially, but also here, you can see individual rocks like that one right there, okay, move back in this shallow arc. And not many rocks get above the height of this tire, or certainly not this quarter panel. A few end up, up around here, but that's because they collide with each other. But otherwise, they almost all go straight back. And this rear tire, as you can see there, is shooting rocks as well, independently of the front tire, and that's how they go. Okay, so the arc that they were tracing is similar to this one here, maybe a little higher. And these are all parabolic arcs. The only difference is the amplitude, the height and the distance. So I'll just read this here. Projectile motion is a form of motion experienced by an object or particle, in other words a projectile, that is thrown near the Earth's surface and moves along a curved path under the action of gravity only. In particular, the effects of air resistance are assumed to be negligible. This curved path was shown by Galileo to be a parabola. The study of such motions is called ballistics, and such a trajectory is a ballistic trajectory. And here is this trajectory traced by this water, this stream of water. And the typical, or I should say the prototypical example is a cannonball, because a cannonball is so massive that the air resistance is going to be negligible, because what we're talking about is the relative mass of the cannonball and the air. There's a large difference. So this is the parabolic trajectory that we're talking about. Now watch what happens with the sand here on this beach and with this dune buggy, the sand particles as they're shot from under this tire here. This is something completely different. They are not tracing paths, trajectories straight back like the rocks did. And that's because the sand is much lighter. So relative to the air, they have much less mass. And therefore they encounter very significant air resistance. And they bunch up here. The lead sand particles are slowed down by the air. They run into a wall of air all around the tire. And then the particles following the lead ones collide with them and bunch up. Okay? And that's why you get this concentration. But they still have energy, kinetic energy. And so they hit each other, and they have to go somewhere. They go up. Okay? And this, is, in fact, is a classic, or both of these, are classic rooster tails. These guys that do these things, play around with these dune buggies and such, that's what they call them, rooster tails. Here you see, as this dune buggy moves, that it shoots up numerous rooster tails, vertical columns of sand. And the sand sits up in the air, in dust clouds, and then just settles gradually down, back, almost straight back down. In this video, you see even more closely what happens right from the beginning. The sand particles run into literally a wall of air. It's like a viscous fluid of air around them, around the tire. And so they don't go straight back at all. They form these classic rooster tails vertically, like so. And here you see the multiple columns of sand, in this case with this motorcycle, and the sand dissipates suspended in the air, and then settles gradually straight back down, pretty much, like so. So these trajectories are very different. They're trajectories with linear air resistance. They're not parabolic trajectories. They're not symmetrical at all. Not like that. Okay, so let's compare this lunar rover on the moon with what we just saw with that dune buggy on Earth. Okay, this should be very different, of course, because they're in a vacuum. And by the way, this particular scene is from Apollo 16. They were racing around and showing off what they could do with the lunar rover. So here we go, and what you see is nothing more or less than the exact same phenomenon. Okay, it's not, the parameters again are gonna be different. The height of the particles, the exact quote unquote specification, so to speak, but the overall phenomenon is the same. A rooster tail, a vertical column of sand, suspended. It becomes suspended in the air and settles down very gradually. It is not, these particles are not exhibiting shallow trajectories, parabolic arcs at all. And here you see the classic arc of a forming rooster tail, and there it goes, gets bigger, and then settles down. The dust settles down gradually. And here's the multiple columns of sand in multiple rooster tails. And there's another example of a nice big rooster tail. It's the exact same general phenomenon of how sand particles, because they're in sand, fine sand, how sand particles behave in an atmosphere, okay, in air. They were not on the moon. The behavior of the sand or dust in the case of the lunar rover is essentially identical to that of the dune buggy on Earth, complete with prominent vertical rooster tails. But this would not be so if the lunar rover were really on the moon. The particles would, despite their low mass, instead shoot straight back in low parabolic arcs like the rocks of the four-wheel drive car, since they are launched from a similarly low point on the tires. In a vacuum, the mass of a projectile is irrelevant to the basic shape of its trajectory. All projectiles move in symmetrical parabolic arcs, since there is no air to offer resistance to their motion and cause their trajectories to deviate in any way. Without question, the lunar rover, quote unquote, is being driven on Earth. Okay, moving on to gravity. The Earth is much larger than the moon. This is something that probably a lot of people don't quite recognize, because we look up in the sky and we see a large moon, or what we imagine is a very large moon, especially near the horizon. And also in the sky, it's the moon is the same size as the sun, which we know is huge. So we imagine that the Earth would look more or less the same, but in fact the Earth would appear much larger, because in fact the Earth is much larger than the moon. And the mass difference is huge. The Earth is 81 times more massive than the moon, or in other words, the moon is only 1.2% of the mass of the Earth. And this translates into a moon gravity of only 1/6 that of the Earth. And here is the difference in size, graphically illustrated. It's like a basketball to a tennis ball. But whereas a basketball is less dense than a tennis ball, the Earth is actually more dense than the moon, because the Earth has a solid iron core, whereas the moon is just rock throughout. So the average person on Earth, especially a young, fit person, can easily jump 1.5 feet or 2 straight up on the Earth, like so. And here's this chart which shows that the average man, or the average jump of an average man, is 1.5 feet. Okay? And professional athletes can jump quite a lot higher than that. In fact, they can jump over 3 feet straight up. Now here's an average man. We're going to take this person as an average man, probably about 180 pounds. This is that actor, by the way. I forget his name. He did James Bond movies, I believe. But anyway, now how much would he weigh on the moon? If he weighs 180 pounds on Earth, he would weigh 30 pounds on the moon, 1/6 of that. And that's equivalent to a 5-year-old boy. Okay? So he weighs 30 pounds on the moon, but he has the body of a 180-pound person, a strong man. So he would be able to jump 6 times as high because he's only carrying 1/6 the weight he would carry on Earth. So 6 times the 1.5 feet that he could jump on Earth would be 9 feet. He would be able to jump 9 feet up in the air. Not in the air, the moon has no air, but straight up, okay? Now, how high would an astronaut be able to jump on the moon carrying a heavy backpack? Okay, now this backpack weighs about 120 pounds. So now a 180-pound man weighs 300 pounds, and all the astronauts were roughly average height and weight. So you're carrying 300 pounds, but it only weighs on the moon 50 pounds because you divide 300 by 6, which is the weight of an average 7-year-old boy. So you have a 180-pound man, a strong man, carrying only 50 pounds. He should be able to jump about 4 times what he jumps on Earth. Okay, so he should be able to jump over roughly 6 feet. He should be able to jump like this. And by the way, that photograph that I showed you, this whole scene, this whole sequence, is from John Young's famous jump salute in Apollo 16. Okay, so he was demonstrating either, maybe not explicitly, but implicitly, the low gravity on the moon. But he failed entirely because this is how high he should have been able to jump. Okay, it should have been very dramatic, completely unmistakable that he was in low gravity. Now watch the actual jump. That's as high as he got. He jumped a normal 1.5 feet. In other words, he was on Earth. He was definitely not on the moon because he definitely would have jumped much higher on the moon. In Wernher von Braun's book, Conquest of the Moon, which, by the way, is a much more realistic depiction of what a real moon voyage would be like than Apollo, this is what he said. Our movements are restricted by the cumbersome suits, yet we will feel light. The moon's gravity is 1/6 that of the Earth, so a 180-pound man weighs only 30 pounds. We will wear weighted shoes to help pin us down. They would need to have weights to hold them down, otherwise they would go too far and too high. But look at the jumps on the Earth. Here's another one. The guy jumps a normal height. Did I say Earth? On the moon, yeah. He's supposed to be on the moon, okay? But he jumps the height of the same height as he would on Earth, more or less. That is not an abnormally high jump by any stretch. And you can see the same thing. You see the same thing when they're walking and running as well. So here you see this astronaut hopping along. They do this little hop to make it look a little bit unusual, but clearly, and I'll run it backwards, or run it back and we can see it again. His feet do not get up high. They are just inches above the ground, okay, which would not be the case on the moon. It is the case on Earth, but it would not be the case on the moon. So here's what Gerard Wisniewski says, explaining what's going on. With less gravity on the moon, the strides would above all gain in height and length, and they do not. The strides are slower without becoming higher or longer. This would suggest that the photos were shown in slow motion. When speeded up, they immediately begin to look natural, in other words, earthly. So in some of these videos, like this one here, What Happened on the Moon, they actually go through the famous jump salute and other sequences, but they show them at normal speed. And they speed up the obviously slowed down moon film, and then they run that, and it appears completely normal. I'm not going to show you the video sequence, but the jumps become completely normal, as do the runs. Okay, in this video here, you can see these guys running after they've speeded up the film, and they look perfectly normal. And this is what must have been done, because if they had been on the moon and you had speeded up the footage of them on the moon, it would have been even more abnormal. Okay, at normal speed on the moon, they would have been jumping way higher and way farther than on Earth. And if you speeded it up, they would have looked like Superman. They would have looked like they were flying above the surface of the moon. Instead, when you speeded it up, they looked like they were on Earth completely. So slow motion was the key. It gave them a bouncy, floaty feel, or at least it looked that way. And this was the key to the illusion. So this is the kind of thing that we saw on TV. And I'm just going to show frames from the film. It looks slow and floaty. Okay, this is what it would look like at normal speed. Okay, it would look completely like a normal jump. That's the same basic sequence, except that I used a whole lot of frames in this one. Okay, and then I used a few frames to simulate simply a faster speed in this one. Okay, that's all it was. It was just playing with the speed of the film. Neither of these jumps is an abnormal jump at all. It's an earthly jump. All indications are that these astronauts, these so-called astronauts, were in Earth gravity, not moon gravity. And they had a few other alleged demonstrations of low gravity. At one point, they hit a golf ball, supposedly, except that they didn't show where the golf ball went because the camera was fixed on the lunar rover and didn't follow the ball. The astronauts said, "Oh, it went miles and miles," but we didn't see that. They did the drop of a hammer and a feather, one in each hand, but that demonstration has been reproduced on Earth. It depends on the density of the feather. I did that experiment myself. If you have a fluffy feather, it'll drop slower than a hammer. If you get a dense feather, it'll drop the same speed as a hammer. And who knows that they didn't use a plastic feather, for all we know. Okay, so that doesn't demonstrate anything. And then at another point, they threw a hammer, this small hammer that they used for their geological work. They threw that, or one of the astronauts threw that, but from all appearances, it looked like a 30 to 50 meter throw, which would have been perfectly normal in Earth gravity. It did not go hundreds of meters, which is what we would have expected on the moon. So the point is that they definitely were not on the moon. They were not in moon gravity. Radiation. These are aurorae. That's plural for aurora, also known as northern lights, except that they also occur at the South Pole. And they're very beautiful. If you've ever seen a good display, you won't forget it. And what it is energetic particles, radioactive particles, coming from the sun and hitting the Earth's atmosphere. So they demonstrate that radiation, space radiation, is a reality. There's no question whatsoever about it. And the first confirmation of this was in 1958, I believe, when the Explorer satellite went up, this satellite here, and it carried a Geiger counter. I believe that's how you pronounce that, Geiger counter, which measures radiation. And the radiation was so strong that it knocked out the counter. The gauge went off scale. And Ernie Ray, one of the scientists involved with this Explorer launch, said, "My God, space is radioactive." And indeed it is. So there are three types of space radiation. There are particles trapped in Earth's magnetic field, there's solar particle events, and there's galactic cosmic rays. And this is a more colorful illustration of this. These are the galactic rays. This is the Van Allen belts, which I'll explain in a second. And this is the solar particles coming from the sun. So, galactic cosmic radiation. Distant supernova explosions are thought to be the source of these high-energy ions. They travel across the galaxy at close to the speed of light and can easily pass through the walls of a spaceship. With current technology, at least, they cannot be shielded against. Trapped radiation. Earth's magnetic field can trap charged particles from the solar wind. They become confined to the Van Allen belts, two donut-shaped magnetic rings encircling the planet. This type of radiation does not pose a threat unless astronauts travel through the magnetic field, but they, in fact, have to. Solar energetic particles. These high-energy particles are released by the sun during periods of intense activity known as solar particle events. Although these events are hard to predict, astronauts and vulnerable equipment can be protected from this form of radiation using shielding materials. This kind of shielding, though, is extremely massive, or would be massive. That's why it's never used. So this whole business of protecting astronauts with shielding material is completely theoretical. In practice, it's impossible. And Apollo had no such shielding. So this is the Van Allen belts. There's an inner belt close to the Earth. Okay, that one right there. And the outer belt. Now, another indication of the reality of the Van Allen belts and space radiation in general is that we actually encounter it. Earth satellites actually encounter it at the South Atlantic anomaly, this point right here. And the reason is that the Van Allen belts are asymmetrically distributed around the Earth. And that's because the magnetic axis is off center. Okay? It's not the same as the rotational axis. So because of that, one of the spots of the inner Van Allen belt comes very close to the Earth. In fact, it's called the South Atlantic anomaly because it's right there in the South Atlantic and over Brazil. And this is a more dramatic illustration of that. The closest radiation belt to Earth roams above South America. It is called the South Atlantic anomaly and gives off high levels of radiation that has been known to destroy satellites. And these are some of the satellites it's destroyed: the Terra satellite, the Nozomi satellite, the CSAT satellite, and the Yamal satellite. Okay? And it's done other damage to other space vehicles as well. Now, moving on to the solar particles. This is a prominence. Okay? This kind of thing happens during the sun's magnetic storms. And these storms happen on a cycle, an 11-year cycle. They intensify over a period of 11 years. Now, this, as I said, is just a prominence. That's not the actual particles that fly all the way to the Earth. You can't see those. Those are atomic sized particles. And this is a graphic illustration of the size of these storms. This is the Earth to scale. Okay, the storms themselves are much larger than the Earth. So a huge number of particles travel from the sun to the Earth. However, we are protected from these solar particles by our magnetosphere. Okay, this is practically a a force field, literally, that shields us from the oncoming dangerous particles. Now, the Van Allen belts are much closer to the Earth, and they don't shield us, but we aren't bothered by them as long as we don't travel through them. So we're protected in this cocoon of ours. And as I said, the storms follow a cycle. It's also known as the sunspot cycle, or the solar cycle. And it's an 11-year cycle, and one of those peaks was right at the Apollo missions, the Apollo moon landing missions. So the astronauts would have been, if they had actually gone, would have been subjected to thousands of solar flares. Here are the numbers here. During 1968, or rather 69, 70, 71, 72, thousands of solar flares. Now the flares vary in intensity, but some of them are and would have been deadly to the astronauts. They received, on average, about 150 flares, or they experienced an average of 150 flares each on each mission. As again, some of those would have been deadly for sure. As John Malden says, and I'm going to quote from a few books here, and notice the dates. Okay, this is all long after Apollo, so this problem of radiation persists. Apollo did not solve it. So John Malden says, cosmic particles are dangerous and require at least 2 meters of solid shielding around all living organisms. Solar flares can give doses of hundreds to thousands of rem over a few hours. Such doses are fatal and millions of times greater than the permitted dose. Neil Commons says, you will face much, much more radiation in space than you do on Earth. Galactic cosmic rays will continually bombard your body and cause cellular damage. Solar energetic particles cause serious illness and death. Van Allen belt particles cause irreparable damage to living tissue. No reasonable quantity of known material will stop all these rays. This person, Leonty Miroshnichenko, says solar storm shelters, that is, special thick-walled rooms, will be necessary both on the transit spacecraft and on the planet's surface. But the design of radiation shielding for a spacecraft is very difficult. Now, and the more realistic accounts of a future voyage outside of Earth's protective cocoon all talk about these storm shelters. But they would be, this is a vast understatement. They wouldn't be just very difficult. With no technology, they are impossible because they would require, they would be very massive, and you wouldn't be able to get a ship off the surface of the Earth with the required thick walls of a storm shelter. Yet that's what would be necessary both on the bodies that they would visit, like the moon, as well as in transit. So the whole thing, with our technology, space travel is an impossibility, period. Now, von Braun, more realistically, what he says that his astronauts would do, not his astronauts, of course, but what astronauts would do when they get to the moon is immediately get into shelter, okay, into a large crevice where they would be able to build their bases, and they would be protected both from the radiation as well as micrometeorites. Compare that practical, sensible practice with the Apollo astronauts who saunter around, prance around the moon without a care and completely exposed to both deadly radiation and deadly micrometeorites. Never was any kind of problem reported by the Apollo astronauts. Another indication of the unreality of Apollo is that the Soviets were always ahead in the space race. And here's a long list of firsts. They had the first satellite, the first spacecraft to the moon, okay, the first man in space, of course, first spacewalk, etc., etc., etc. So why didn't they reach the moon before the Americans? In 1963, Soviet space scientists told the famous British astronomer Bernard Lovell, in connection with their lack of plans for a lunar landing, that they, quote, could see no immediate way of protecting cosmonauts from the lethal effects of solar radiation. Viktor Bazykhin, a Soviet astronomer, says the information obtained with the aid of Sputniks, rockets, and balloon probes has proved beyond all doubt that radiation is the chief obstacle to penetration of cosmic space. The National Research Council, okay, in 2008, this is what they wrote: exposure to the space radiation environment outside of the protective magnetic field of Earth presents a risk with which humans have limited practical experience. What on earth are they talking about? What about Apollo? There was hardly any mention of it. Having a vexing discussion about the conundrum of space radiation today is like worrying in the 16th century about how to sail across the ocean to another continent when the voyage had already been completed numerous times and mastered by Columbus and others in the 15th century. It's absurd. If Apollo had been real, the radiation issue would have had to be resolved then. The problem still exists now because it was never tackled. And this, of course, is because Apollo was a fairy tale. Here are some damages to the body caused by space radiation. Cataracts and damage to the eye, increased cancer risk, damage to the circulatory system. I'm not going to go through all of them, and this isn't even a complete list here. Skin damage, damage to muscles, cartilage, etc., etc. Okay, and why is this? It's very simple, because radiation kills cells. All right, cell death, dead cells, and it breaks down the body. Yet, these 12 astronauts are supposed to have walked on the moon, and 12 others are supposed to have made the trip. And even though they didn't walk on the moon, they would have been subjected to about the same amount of radiation, and all of them lived normal lives without any effects of radiation either during the trip or immediately afterward. No radiation illness or anything of the sort. In fact, they all have lived, almost all have lived long and healthy lives. The average age at this point in time is 80, and more than half of them are still alive. So there's no indication whatsoever that they had any encounter with any space radiation, and that's because they didn't go anywhere. In fact, we can't leave our protective magnetosphere cocoon. If we do, we're fried with our current technology.